Okay, welcome to Class 8 of Physics 350. This is Work and Energy in Electrostatics, covering Section 2.4 of the textbook. And we'll start off with a single charge, electrical work and potential energy for a single charge, and build up from there to multiple charges and to continuous charge distributions. But starting with a single charge, remember that the work, any kind of work, is the line integral of the force. So the electrical work would be the line integral of the electrical force, Fe, from point A to point B in a electric field E. And then the electrical force is equal to the charge on the charge which is present times the electric field. But then notice that if we pull out the charge Q, we have the integral from A to B of E dot dl, which is related to the electric potential, which we saw last time. In fact, the electric potential is minus the integral from A to B of E dot dl. So if we pull out a minus Q, we have minus Q times minus the integral from A to B of E dot dl, and this here is what we defined as the difference in electric potential between points point B and point A here. Okay, so our electrical work would be minus the charge Q that was following this path times the electric potential at point B minus the electric potential at point A. In addition to work, we like to define potential energy. And you may remember that potential energy is related to work. Potential energy is stored work. So if we do electrical work, positive electrical work on something that is, if we do negative electrical work on something, that's going to store electrical energy that we can later recover and do useful things with. So electrical work here is minus Q VB minus VA, and the change in electrical potential energy then would be the negative of that, or Q times VB minus VA. Okay, so we just found that the change in electrical potential energy is proportional to the charge and the difference between the electric potential at the starting and ending points. For a point charge, let's take a point charge as an example. For a point charge, we'll call the point charge 1, and then the charge which is in the neighborhood of the point charge 2. So Q would be Q2, and V, the electric potential, would be V1, the electric potential of the point charge. V1 at the location of our second charge minus V1 at our reference point for the potential of the point charge, which is at infinity. So, and we know that for the point charge, we set the reference at infinity. So we have Q2 times Q2, the charge which is experiencing the field, times V1, the electric potential of the point charge at the location of that charge. And so we can write that out as Q2 times what we know to be the, we derived last time, the electric potential of the point charge is 1 over 4 pi epsilon naught Q1 over R. We called it R last time, now it's R12 for the distance between charges 1 and 2. And then if we like, we can move Q2 in with Q1 to make a nice symmetrical formula. 1 over 4 pi epsilon naught Q1 Q2 over R12. And you can see that here, just using different notation. Instead of Q1 and Q2, we have capital Q and lowercase q, and instead of 1 over 4 pi epsilon naught, we have K. So the electrical potential energy is K Q over R, or 1 over 4 pi epsilon naught Q1 Q2 over R12. Okay, what about 2 or 3 charges? Well, let's start off with a single charge. If we have a single charge, we don't have any potential energy because we don't have any interaction with any other charge. So that, let's just establish that there's no intrinsic electric potential energy for a single charge. With 2 charges, we have just done that basically because we can treat really either one of them as a point charge. We treated one as the point charge. So this is what we just did on the last in the last slide. Q2 V1 of R2, going through the same steps. And so we have for 2 charges, the electric potential energy is 1 over 4 pi epsilon naught Q1 Q2 over R12. Okay, so it's proportional to the Coulomb's constant. It's proportional to each charge, and it's inversely proportional to the distance between them, the potential energy. What if we add a third charge? So what if we have 3 charges? Okay, well, each of the other 2 charges, charge 2 and charge 3, are going to feel the influence of, the third charge is going to feel the influence of charge 1 and charge 2. So we would say that the change in the electric potential energy is going to be charge 3 times the total electric potential at the location of charge 3, which will be the charge 3 times the electric potential of charge 1 plus the electric potential of charge 2 at the location of charge 3. Okay, so we know what these are again because we're assuming these are point charges. So V1 at the location R3 is going to be 1 over 4 pi epsilon naught Q1 over R13, and V2 will be Q2 over R23. Okay? So we're basically adding in 2 terms because the third charge is going to interact with each of the first 2. Okay? For 3 charges, we take the amount we had for the 2 charges up here, and we add in the change that occurred when we moved from 2 to 3 charges. So that's going to be, if we look here, the way we've set this up, 1 over 4 pi epsilon naught Q1 Q2 over R12, and then if I distribute this Q3 in here, we get 1 over 4 pi epsilon naught Q1 Q3 plus Q2 Q3. So this is a nice symmetrical formula, as it should be, because none of the charges are special or different from the others. They appear symmetrically. We have all possible pairs, Q1 Q2, Q1 Q3, and Q2 Q3 over the corresponding distances. Okay, so this would be the formula for the electrical potential energy of 3 charges. Okay, what if we go to more than 3? In fact, what if we go to n being some larger integer, discrete charges? So we're talking about point charges here. Okay, well, let's just review what we just found for the 3 charges. It's the 1 over 4 pi epsilon naught times this factor Q1 Q2 over QQ over R for each pair of charges that appear. Okay, so get ready for a little bit scary looking sum at first, but let's make sense of it. So if we generalize to n discrete charges, we're going to have the 1 over 4 pi epsilon naught as our overall constant. We'll have this Q over R for each pair of charges. And the way these sums work is the first sum goes from 1 up to the number of charges, and the second sum goes from the integer above the first sum up to n. Okay, so let's, just to make that clear, let's apply that to the case of 3. So if I is going from 1 to 3, if I is 1, then j could be 2 or 3, since j greater than I up to n would be 2 or 3. So we'd pick up Q1, Q2, and Q1, Q3, and then I would go to 2, and we'd pick up j greater than I would be just 3, and so we'd pick up Q2, Q3 here. And if I is equal to 3, there are no j's which are greater than 3, so we don't pick up anything. Okay? So hopefully that helps you see why this formula, this double summation formula, when applied to n equal 3, produces this result up here. Okay, well, we're going to do a little bit more hocus pocus. We're going to change the summation a little bit by introducing some double counting. What that means is that instead of taking the second sum and just taking the terms which are greater than the index of the first sum, we're going to take all the terms in the second sum which are not equal to the term in the first sum. Okay. So, for example, for I equals 2, in the case of three charges, for I equals 2, we wouldn't just take j equal 3. We would take j all terms which are not equal to 2, so 1 and 3. And for I equals I equal 1, we would take j equal to 2 and 3, and for I equal 3, we would take j equal to 1 and 2. So basically, we're taking all different combinations of I and j, except where we count I, except where I is equal to j. And that, compared to the first sum, that introduces what's called double counting, because we're going to get, for I equal 1, we'll get a j equal 3, and for I equal 3, we'll get a j equal 1. Whereas we don't want that to appear twice. So therefore, we have to divide what we had before by a factor of 2, which is why this becomes from 1/4 to 1/8. Okay? Okay, so you may have to stare at these sums for a little bit to convince yourself that what I'm saying is valid, but it's I think the logic is clear if you replay this and think about it a little bit and compare it to the 3 charge case. Then we're going to go ahead and factor out this sum. Notice that the j sum doesn't depend on I, so we can pull qi out in front of just the I sum. And then we'll pull that factor of a half, which we were talking about, out in front. So we have 1/2 times the sum from I equal 1 to n of qi of what's left, which is 1/4 pi epsilon naught times qj over rij. But that is the electric potential of a point charge qj, right? Q over 4 pi epsilon naught r ij, where I is the charge experiencing that. So, or kq over r. Okay, so you want to use k instead of 1/4 pi epsilon naught. All right, so so this right here is the sum over all charges, not including the ith charge, the current charge we're considering, of the electric potential. And so we can just call this 1/2 the sum from I equal 1 to n of qi times the electric potential at the location of I of all the other charges, okay, which we just write as V of Ri if there are a lot of charges. Okay, so so this is the formula for discrete n charges, where V is understood to be a total over all of the charges in the system, this V here. So we could call this V total if we wanted to. All right, so as if that weren't enough, let's try, let's try to think about a continuous charge distribution. Oftentimes, we approximate, for example, the charge in a molecule is spread out in space. The electron charge distribution is spread out in space. We don't want to treat it as a point charge, so we want to treat it as a continuous charge distribution. So we'll start off with the formula for n charges, which we just established. This 1/2 factor to prevent double counting times the sum of Q times the electric potential at the location of each charge. And then here's a picture of a continuous charge distribution, or a continuous sort of blob of charge with a little bit of charge dq, and dq is going to be equal to rho, the charge per unit volume, times dv prime, where dv prime is the volume of this little box here, okay? And that box can be anywhere throughout the continuous distribution of charge, okay? So, therefore, qi, our charge, becomes dq, and dq is rho times dv prime. And then we have v still as v of Ri will become v of r prime, because r prime is the variable which indicates the source of the charge distribution. It's the prime variable indicates that's where the charges which are producing the electric potential here at the point P. Okay, so we can interpret the electric potential energy as contained in the interaction between charges, as represented by the charge density times the electric potential. So the charge density times the electric potential. The more charge we have over here, the more energy we'll have, and the more electric potential is generated by our source, the more electric potential energy we'll have. But there's a neat other way to interpret the electric potential energy, which is the math behind it is a little bit well, it's something you could follow, but it's a little much to put into a lecture. It's in your textbook in section 2.4. So here is our expression for the starting with our expression for the electric potential energy in a continuous distribution rho. It's what we just had right here in the center. Using a couple of relationships, the first one is that rho is epsilon naught times the divergence of E. You can recognize that as Gauss's law in differential form. Del dot E is equal to rho over epsilon naught. And also the gradient, the fact that the E is the gradient of V. And doing a little fancy math involving triple integrals, okay, and again, I'm not going to show that here. You can see section 2.4. It involves an integration by parts. It's possible to show that we can express the energy in the electric field, the electric potential energy, in terms of the electric field itself. So we just get the 1/2 stays, and we have epsilon naught times the integral over all volume of E squared, the square of the electric field magnitude, okay? Or if you may say, how do you square a vector? Well, you take the dot product of the vector with itself. That's what this e squared really means. So, or if we want to bring the 1/2 epsilon naught inside, we'd have the integral of dv prime 1/2 epsilon naught of e squared at the location r. Okay, so an integral over all volume of 1/2 epsilon naught of r. But this is saying the total electric potential energy is the integral over the volume of some kind of density, okay, of some kind of density. Just like the mass is the volume integral of the mass density, or the charge is the volume integral of the charge density, here we're saying the electric potential energy is the volume integral of this quantity here. So we can interpret this as the density of electric potential energy. That is, we can interpret this 1/2 epsilon naught e squared r as the electric energy per unit volume. So just to conclude, there's kind of two ways we can look. In the continuous case, we can look at the electrical potential energy as being stored in the electric field. And the electric field, then we have this expression, the electric potential energy is 1/2 epsilon naught e squared of r, or so it's stored in the field itself, which is created, or we can look at it, as we looked at it before, as being stored in the interaction between the charges and the electric potential that are created. So these are alternate approaches. Both of them are equally valid ways to look at the electric potential energy. Okay, so hopefully, the 3 points, I don't have them summarized on a slide, are that for discrete charges, we get a sum of point charge-like terms, but excluding double counting of terms. For a continuous charge, we have these two interpretations where we can either have the interaction between the charge density and the electric potential, or a straight integral over the square of the electric field times this constant. And those both give the electric potential energy in the electric field. Okay, thanks so much, and see you in class.